Welcome to the Hydrocarbon Recovery and Fractionation webinar. If you have just joined, please make sure your mic is muted and your video is off. If you're able to hear me, that's fantastic. I'm joined today with my colleagues Ganank, John Chan, Di Wu, and Omar Mikawi. They are in the chat, so if you have any questions at all, please make sure you chat to everyone. Personal messages to me can only be answered at the end of the session. Okay, let's give it a go. Before we start, I just want to show you guys a little bit about us. We are Bryan Research and Engineering. We provide the software named ProMax. In general, the software is a simulation steady state based software to model your units. One thing that we really focus on is to help our clients remain competitive even in these difficult times. We focus a lot on service on top of our software. So anything big from building models to optimizing them to small, like if you spend more than 5 minutes trying to convert the model, we're there to help you along the way. So let's begin. So let's start with a system overview, because this webinar is one of a series of webinars we have already conducted before. The whole idea of this is to process gas, to clean it up, to separate them out so that we can sell them. We have talked about gas sweetening, removing H2S in our amine sweetening webinar. We have talked about stripping out any acid gases and ammonia during our cell water stripping webinar, removing water to prevent hydrate formation in our dehydration webinar, as well as how to dispose of this H2S when we talked about SRUs. Today, we have extremely clean gas, very little water, very little H2S and CO2, and we're talking about fractionation and hydrocarbon recovery. So the goal of all this is obviously to make something we can sell. You can't sell anything unless it meets certain specifications. And here on this list are some of the typical specifications that you might see for pipeline gas. The top one you will notice, water content, we are covered. H2S and CO2 often are removed using amines, which we have covered as well 2 weeks ago. Next week, my colleague Ganank will be covering how to treat more difficult sulfurs like mercaptans using caustic treatment. And of course, today we're talking more about our gross heating values, hydrocarbon dew points, and delivery pressure. Of course, these are very important values. If you can't really sell gas that doesn't have much value per volume. And when it comes to the hydrocarbon dew point, you don't want any liquids to be forming in your gas lines, because this will build up in certain areas and cause issues down the line. Of course, depending on where you are, we might also have a delivery pressure requirement where you have to pump up to maybe somewhere super far away where you need a higher delivery pressure in that case. These numbers, for those of us more experienced, will look kind of typical. For others, it might not be that obvious what the benchmark is. So let me show you an example feed. This feed has a composition of 74% C1, 11% C2, 8% C3, and a bunch of other heavier hydrocarbons. You will see straight away that the heating value is way above 900, which is quite good. Its pressure is okay. We don't really have to repressurize it. However, you'll notice that the dew point is very, very high. So if we were to pipe this into our gas lines, you will notice that you get a lot of liquid dropout, which is not what we want. Also, in order to fix this dew point, we will have to, of course, knock out the heavier hydrocarbons. As an added benefit to this, a lot of these heavier hydrocarbons, apart from methane, have their own individual uses which often, not all the time, often have a higher value add compared to just burning the methane. For example, ethane is a very popular petrochemical feedstock, and isobutane is used a lot for octane number blending and refinery stuff. So let's talk about the very first way of fixing the biggest problem, our dew point. This is a basic JT valve skid. At the start, you'll see some basic heat integration, followed by a JT valve, and then separation occurs in the LTS, the low temperature separator. The point of the JT valve is to cool the gas via the Joule-Thomson effect. After the gas is cooled, the low temperature separator will remove any C3 plus below. Now, your next question might be, what is the Joule-Thomson effect? And we'll have to talk a bit more about thermodynamics during this class to allow you to visualize what's going on when you expand the gas. So let's show it to you in terms of a phase diagram. Personally, I really like phase diagrams because it allows me to visualize the entire process. They are very specific to your composition, and this whole graph you see before you is completely generated by ProMax. So if you have a gas composition you're working with and you want one of these automatically generated, just drop us an email after the session and we can work on making one of these specifically for you. Okay, so now that I have this graph, how do I read it? Well, let's read it by going through an example. In this case, I'm going to start at this red point. How do I read the temperatures and pressures, etc. of this point? Well, let's start with the temperature. You will notice on these lines, we have isotherms. So along each of these lines, the temperature is constant. You will notice that the red dot is somewhere in between 38 and 65 degrees Celsius. If I draw a line, I would say it's roughly 42 degrees Celsius. How about the pressure? I just have to look to the left and you see I'm roughly 1000 psig or 69 bar gauge. Now, what happens if I put this particular point through a JT valve? Well, a JT valve goes through what is known as isenthalpic expansion. Isenthalpic just means constant enthalpy. At the bottom, you'll notice the x-axis is enthalpy. So if I were to draw a vertical line down, it would be exactly isenthalpic. So in this case, this JT valve drops me from 69 bar gauge to 14 bar gauge. And as a result, the temperature goes from 42 degrees Celsius down to 10 degrees Celsius along this isotherm. Now your next question might be, okay, so the more pressure drop I get, the cooler it is. And in general, the cooler it is, the more liquid I have. Well, the more liquid I have also has a different effect, which I'll be showing it to you on ProMax. But you have to note that there is this curve over here called the maximum liquid curve. This will be shown more, but I want you to remember the conditions that we're going to represent on ProMax in a second. We're starting at 42 degrees Celsius, 69 bar gauge or 1000 psi, and we're dropping it down to 200. So allow me to jump over to ProMax. And we'll start off with what one of these JT skids might look like. These are often just skids that you can just buy off a company and just truck it in and attach it to your plant. You'll see here there's heat integration, the low temperature separator, as well as the valve somewhere around here. It's all generally insulated. Okay, so I've overly simplified this skid into just 3 parts: the JT valve, the low temperature separator, and the sales gas recompressor. This is all in ProMax, as you can see over here. ProMax is based off of Visio. So any of the Visio features you are familiar with, you can, of course, use them, such as drawing text boxes, containers, etc. In addition to that, we also have our thermodynamic information behind it. So let me walk you through specifying such a simple unit. We'll start with the feed. Any feed, any inlet in ProMax has 4 degrees of freedom. The 4 degrees of freedom, we'll see how many I've specified already. If I double click into it, you'll see in blue, which means user specified, I've already put in an arbitrary value of mass flow, 100 kilograms per hour. So that's 1 down, 3 to go. Another thing you have noticed is under composition, I've already put in a composition. And this is often from some gas analysis. Lastly, I have 2 more things that I can specify. Of course, the 2 things I would specify in this case is my starting point, which is 42 degrees Celsius, and 1000 PSIG. Now that I have all four degrees of freedom fulfilled, you will notice all the other information populates. That is because with just 4 pieces of information, we're able to calculate everything else about that stream. And as a result, the stream now turns green. Next, every time you add a block, that is 1 extra degree of freedom. So 1 extra degree of freedom just means we can specify one thing, and everything else will be specified for you. So in this case, I know that I'm dropping it from 1000 PSIG to roughly 200 PSIG. So I'm just going to put in 200 here. You'll notice everything else is calculated for me. Same thing with this vessel, 1 block, 1 degree of freedom. I'm just going to specify a pressure drop of 0, assuming that most of the pressure drop occurs across the JT valve. And everything becomes green as well. As for the sales gas recompressor, we have 1 degree of freedom from the sales gas recompressor itself, and we have 1 more from an energy stream. Every time you see energy stream, generally that means we have 1 more degree of freedom. So the first obvious one, I'm just going to say I will recompress it back up to about 1100 PSIG. And the second degree of freedom, which is less obvious, is the efficiency. Under the recompressor, I can provide either a polytropic efficiency or adiabatic isentropic efficiency. I'm just going to put a value of 85%, but I want you to remember this term, isentropic efficiency, because this will be more important later on. Okay, with that, you'll see that my model is fully converged, everything is green, but I can't really see a lot of information on the screen straight away. So how do I want to add more information in? So the way you can do that is by going on the left-hand side, ProMax streams, and we have this thing called the callout. It allows you to attach anything into a stream, and by double-clicking it, I'm able to have it constantly update any number I want. So in this case, if I want to show temperature, I click OK. Anytime I make a change upstream, downstream, anywhere, this temperature will exactly read whatever temperature in my LP feed. Okay, so now that we have that done, I have prepared something slightly beforehand where I have added in a lot of all these callouts so you can see everything neatly on the page. Let's go to this page. Okay, so let me just walk you through what I've done here. It's the exact same model, nothing's changed. 42 degrees Celsius, 1000 PSIG, drops down to 200. Everything's fine and dandy. The difference is all these blue boxes allow me to specify things outside of the stream. And I report a lot of recoveries over here, which I will highlight as time goes on. So let's recall back to that graph. We drop it from 1000 to 200. We see a temperature drop of 42 to 10 degrees Celsius. But we have quite a bad liquid recovery of only 4%. Okay, so what if I were to maybe drop it slightly less? So I drop it down to 800 instead. Re-execute the file. Instead of dropping out 800 psig, I'm only dropping 200. As a result, you will notice that the temperature goes from 42 to 36. 42 to 36 is a much lower temperature drop. As a result, you will notice the liquid recovery is no longer 4.1%. It is instead 2.6. You're getting less liquid. However, let's touch about that maximum liquid line. If we were to go back to our slide, you'll see that the maximum liquid line intersects the JT valve line at about 450 psig. So what if I put 450 here? Let me execute the whole flow sheet again. And you'll notice, despite dropping less, the temperature here is not 10 degrees Celsius, it's hotter than that. But my liquid recovery is higher. It's not 4.1%, it's almost 5%. The reason why this happens is because you have two opposing forces fighting against one another. The first force is a lower temperature lets you condense more. The other force is a lower pressure makes your liquid more likely to vaporize again. So that's the whole point of this maximum liquid line. If your goal is to get as much heavy hydrocarbons out of your gas as possible, you will want to follow this maximum liquid line. Okay. So obviously, I have not modeled any heat integration, but generally speaking, with such a process, this heat integration will allow my feed to be pre-cooled to roughly 10 degrees Celsius, let's say. And if I read off that graph, that's roughly 600 psig under my maximum liquid. This amount of pre-cooling and heat integration will allow me to achieve 21% liquid recovery, a very big improvement. And as a result, our dew point temperature now matches the specification. The specification, if you recall, was from -5 to 10 degrees Celsius, generally speaking. However, you will notice that my liquid still has a lot of methane, and my propane recovery over here is only 36%. I'm not taking out much propane at all. So the next step on this is if I cannot get it cold enough just from its auto refrigeration with the JT valve, what if I just put in external cooling, external mechanical refrigeration? That's generally done with propane as a refrigerant, and that allows us to drop the feed temperature down to typically -30 degrees Celsius. If I run this again, you will see all of a sudden, the dew point temperature is completely gone because it is no longer possible to condense liquid out of the gas at that pressure with just temperature. And you'll notice my propane recovery now improves to 85%. That's a lot more propane I'm not wasting away. However, you will also notice that the methane in my liquid is 40%. A lot of my methane is still leaking out. I want you to hold on to that thought as I go back into my slides and show you the next part. We just talked about using external cooling, and this is what it will look like on a schematic. You have the same heat integration that can typically get you to 10 degrees Celsius, and then you have some chiller to cool it down. Using this chiller, you can get propane recoveries up to 90%, as I said before. However, this still has poor C1 recovery in the gas and poor C2 recovery in the liquid. as you've seen before, a lot of the methane that we could be selling is still going down with our NGL. So before we move on, I want to bring up the fact that what is this refrigeration that we're doing? Well, typically, we are using some sort of mechanical refrigeration loop, and we generally use propane. But why do we use propane? Why not ethane? Why not butane? Why not methane? Well, it's to do with how economical it is. For example, propane, the red line over here, if we want to cool it, if we want to condense it, we're able to do that at 50 degrees Celsius, which means an air-cooled exchanger is completely capable of performing the job at 17 bar gauge. And if we drop it down to almost atmospheric, we can quite easily get negative 30 degrees Celsius. So we can get a very cold temperature and, 16 bars of pressure swing across the condenser and the evaporator. In contrast, if we were to look at, for example, ethane, C2, the blue line, you will see that we can only reach 32 degrees Celsius at 47 bar gauge. And even then, it's quite difficult for air-cooled exchangers to condense this down, especially in the hotter countries. Yes, we can get a lot colder temperatures, but this huge pressure swing is generally not desirable and not practical. On the other hand, if we look at isobutane, down here on the green line, we get a much lower pressure over here. We can cool it down with an air cooler much lower down. However, if we look at the other end, even at atmospheric pressure, we are only able to achieve negative 12 degrees Celsius. We can't go anywhere as cold as propane can. So this is why we generally use propane for these kinds of applications. Negative 30 degrees Celsius is generally cold enough, and this pressure swing is not too bad. Next, remember how I said, there's a lot of C1 in my liquids? Well, one way to fix this problem is to simply use a stabilizer. A stabilizer takes in liquids from the LTS, adds in a bit of heat, and this heat will allow us to strip out the C1 while keeping the C2, C3, and C4 plus in my liquid. This stabilizer overhead gas, which is typically mostly just methane, will generally be recycled back into the inlet of the whole gas plant so that you're not wasting any of your feed. This system typically operates under these conditions, which will be highlighted more when you have to model such a unit. Okay, so that solves two problems. Let me go back to ProMax. The first problem it solves is, okay, now my methane over here will go back up into my sales gas. However, it doesn't solve the problem where my ethane in my sales gas doesn't go back down, because all we're doing is adding heat here to bring stuff back up. So how do we solve that? Okay, we solve that problem with what is typically known as a turbo expander plant. This is a typical arrangement of it. It's a bit oversimplified, but the whole purpose of this is that ethane recovery requires severe conditions, generally an overhead temperature of much colder than negative 73 degrees Celsius. If you recall, our refrigerants can't get that low. So what do? Well, we will employ this technology instead. It looks very complex, but let me break it down for you. We have the first part of what we discussed. We have some form of heat exchanger network that provides pre-cooling, LTS over here, followed by a JT valve. So that's the simple refrigeration JT setup that we have discussed before. At the bottom over here, we have a column, and part of the liquid goes to some reboiler to strip out. Oh, that's just the stabilizer that we just talked about. All it does is to strip out any methane that ends up at the bottom. So literally the only difference in this system is this turbo expander part. And why don't we just use a JT valve? Instead, we use an expander. I'm going to show you why using another phase diagram. This phase diagram is slightly different because we're not taking the full feed. As I said, it's very specific to the composition. We're only using the vapor. So this only applies for the vapor, which is more or less a lot of methane. I want to highlight these three lines over here. They're the isotherms. The reason why I want to highlight them is because I'm going to remove them. Over here, you will notice the lines now change. I'm now talking about along these lines, they're all isentropic, which means same entropy. The reason why that's important, if you recall, we talked a bit about isentropic efficiency. So let's do it again with another example. We have a JT valve. We're about 900 psig, and we drop it down to about 300. We start at this point. Remember, it's isenthalpic, same enthalpy. It goes vertically down. In contrast, an ideal expander going through the exact same pressure drop from 900 to 300, instead of following the isenthalpic line, it follows the entropy line. The reason why it follows the entropy line is because ideal expander takes out work. And as a result, your enthalpy will drop. But we, of course, assume in an ideal expander that's isentropic, which means it will follow this line precisely. However, in reality, we don't really have an ideal expander. So we have a real expander somewhere in between. Normally, the isentropic efficiency is above 70% to 90%. As a result, we'll experience this line to be a lot closer to the ideal expander than it is to the JT valve. So what's the significance of the different curves and movements? Well, let's bring back the three lines that I removed. You can see we started off at this point, which is something hotter than -45 degrees Celsius. The JT valve drops it down the exact same amount of pressure as everything else. And now we got a cold temperature of -75, which is pretty cool. Not cool enough though, because if we look at expanders, it completely bypasses this -75 line and it gets very close to the -100 degrees line. As a result, we get, with the same pressure let down, we get a much colder process fluid, which means we get a colder top, which means we can recover more ethane. So this is why we want to use an expander instead of a JT valve in that particular location. Of course, you must note that this only works on vapor. It doesn't really work on partial liquids or full liquids because they have a different phase diagram and different isotherms. Okay, so let's talk about how to specify such a unit. It looks very complex, but I'm going to break it down, and I'm also going to show you some of the tricks you can use on ProMax to specify such a unit. Of course, you always start with the end with these kind of units. We start with the end, meaning we look at the specifications we're trying to hit. The fuel gas, we have heating values and dew points we want to hit. And what we call the NGL, natural gas liquids, or Y-grade liquid, generally wants very little C1 per C2. And we have some other information there that basically says, I don't want that much methane in this. So and then when we design it, we start from the left to the right. Okay, let's look at the feed split. We have a split here because we want to use as much heat integration as possible. We want to exchange with the cool gas that comes out of the demethanizer, as well as the relatively cold reboilers. The reason why we generally have 20% that goes to the reboiler and the majority exchange with the gas is because this feed is typically more than 70% methane, which means your overhead flow is going to be 70% of your feed, whereas your bottom flow will only be that 30% to 20%. As a result, you want more or less even type of cooling. So generally you will send 80% to the gas-gas exchangers and only 20 to 30% to the reboilers. Next, let's talk a bit about these exchangers. These aren't the typical shell and tubes, generally speaking. Most modern units use some form of a compact heat exchanger, which allows very close approach temperatures, which is up to like 3 degrees or even 2 degrees apart, to maximize the cooling. Because if you notice in this whole plant, no external refrigeration is required. It is all self-sustaining after it hits steady state. However, you also have to be very mindful of corrosives and mercury because it's made of aluminum typically. And because of its very sensitive nature, you normally take a very long time to start it up because you don't want to thermally shock it. And of course, the small channels makes it easily clogged and is generally more expensive than your bread and butter shell and tube heat exchange. Next, we have already talked about the LTS. In this case, the temperature of this LTS varies depending on what mode you're operating your demethanizer on, whether it's recovery or a rejection of C2. And all it serves to do is separate out the vapor to use the turbine and the liquid to use the JT valve. You have expansion cooling as we have previously discussed with our phase diagrams. We have isenthalpic JT expansion. You typically expect a half a degree Celsius temperature drop for every bar pressure drop you have, whereas an expander you generally have 1 to 1.5 degrees Celsius per bar you draw. From these numbers alone, you can see how much better using a turbine is for cooling down the vapor. Next, the demethanizer itself. There's a lot of information here. I just want to remind you, we'll be sending these slides out to everybody, so you don't have to worry about it. A lot of this information is here so that you can model it on your own after this session. But I just want to highlight two things. First, it says here multiple diameters. It's not very apparent from a ProMax model, but generally speaking, the top of a demethanizer is a lot bigger in diameter compared to the bottom. This is because the majority of these feeds, the methane feeds, are at the top, and this top section, as a result, will have a larger diameter. The second thing I want to point out is notice the temperature difference. At the top, you have a negative 100 plus degrees Celsius, where at the bottom you're about 0. This very drastic temperature gradient makes it so the material choice of your demethanizer is very important. As well, these cold temperature means that you have to be very mindful of hydrate formation and dry ice formation, which is highlighted by our previous webinars talking about hydrate suppression using dehydration, as well as CO2 removal using amines. Next, we have the reboiler at the bottom. All it does is strip out the C1 from the NGL. And in addition to that, typically what you have is side reboilers. The reason why you use side reboilers is because the quality of heat about the middle of the column is a lot higher than the bottom. This reboiler can only cool down your gas at most to 0 degrees Celsius, nothing more. Whereas a side reboiler, around the middle of the column, you might have negative 20, negative 30, negative 40 degrees Celsius, which allows you to cool this feed a lot further. New to this model is vapor subcooling, which uses the gas subcooled process GSP technology. The only difference here is we take a part of this vapor, we subcool it by exchanging it down, exchanging its heat with the overhead gas. And it gets much colder because we don't just depend on auto refrigeration using the turbine. We have some form of external refrigeration that way. This technology allows you ethane recovery from 90 to 95%. And generally speaking, all it does is, the reason why we use a JT valve here instead of a turbine is because this is subcooled, so it will be mostly condensed. And you can't just send everything through it because you won't be able to condense everything out of this. Next, it's not shown here, but another technology quite popular is a recycle split vapor, RSV technology. It just takes a portion of this compressed fuel gas, it sends it through this exact cold gas-gas heat exchanger, drops its pressure to get some cooling, and reattaches it and feeds it at the top. The reason why this is useful is because this fuel gas is almost 100% methane, which means you get a very, very clean recycle and reflux to wash down as much of the C2 as possible. Now that I've explained and presented most of the specifications, let's go on to ProMax to show you how you can specify such a unit on ProMax. Let's start with what it looks like. As I said before, typically your top will have a much larger diameter than the bottom. This is how from far you can spot a demethanizer. You will see the different draws and everything, and most of the heat exchangers are on the ground level. As you can see here, the RSV feed, which is the true reflux, enters into the top. Your GSP, which is the gas subcooled, enters slightly below that. And you have some turbo expander feeds and side reboilers around here. Let's look at ProMax instead. So this is what ProMax looks like. I'm just going to make it slightly bigger by hiding a few of the UI elements. Okay, so how do I specify such a unit? It might look very complicated at first, but generally speaking, we just start from the left to the right, upstream to downstream. Let's start with the feed splitter. Remember I said about 20% goes to the reboilers, so that's feed split 2. I'm just going to say 20% goes to the reboilers. That's that. And everything's green here. And generally speaking, this is where most of the people get stuck specifying such a unit. We encounter this conundrum where I can't really specify this cool feed until I know more about this overhead. And I can't really know more about the overhead until these are all specified so the column can solve. However, on ProMax, we allow back calculation of properties. What this means is we don't always have to start from the start. Let me show you how we can segregate this model so that we can specify this without using a recycle block. It's very simple. We just have to look at this stream right here, cool mixed feed. I noticed straight away that if I were to specify this, the demethanizer, 1, 2, 3 feeds, are all coming from this low temperature separator. So as long as I got this right, everything else should solve down the road. Let me show you this. Under this, you will notice I only have 1 degree of freedom left. And it's some form of temperature. I'm just going to assume that I'm operating this at about negative 28 degrees Celsius. This is my LTS temperature. Straight away, you will see everything here below turns green because I've pre-specified the low temperature separator, as well as given a 33% split over here. Next, I just have to specify the pressures here, here, and here. Remember, the JT valve has 1 degree of freedom. So if I double click onto this, you'll notice it has a blue box over here. What a blue box means is I have pre-set up a specifier. A specifier is just a very convenient tool that ProMax has to automatically update this value based on a rule set you give it. In this case, the rule I gave it is, since this stream feeds into tray 8, I just want you to be the same pressure as tray 8 plus a tiny amount, plus 1. That's all it does. I've done the same for this over here, the top. It's just that pressure plus 1. Okay. Now, the difference here with the turbine is that now I have to specify 2 things instead of 1. I have to specify the pressure, which I can use the same methodology as I did before. But just for demonstration purposes, I'm just going to put 22.41 bar gauge over there. And the turbine itself has an efficiency. Under process data, you will see that isentropic efficiency is given as about 82% efficient. With that, I'm able to converge this block up to here. Now, every single external feed to the demethanizer is now specified. Sorry. For those people, could you please mute your microphone so that everyone else can hear the WebEx session, please? Okay. Okay, let's continue. This demethanizer has 1 energy stream down here, which means it has 1 degree of freedom. Next, you will see that the side reboiler takes out an upper side draw from tray 11 and a lower side draw from tray 16. All this means is I have 1 more and 2 more degrees of freedom. So that is a total of 3 degrees of freedom. These 3 degrees of freedom will be shown within the column. Under specifications, you'll see a number over here, 3. So what kinds of specifications can I give it? Well, let's go with what we generally know about such a unit. Most of the time, these side draws are a full draw tray. And there are many ways of specifying it. But the way I prefer as an approximation, just for the purposes of this webinar, is to use a very high flow ratio. So what are flow ratios? If you double click on it, you'll see flow ratio 1 relates to the upper side draw. And it's just a ratio of how much liquid goes below the tray and how much liquid is sucked out of the tray. If I put a very high value, for example, 50, it means for every 1 kg that goes past the tray, 50 kg will be drawn out. And this will be very specific, and this will allow us to basically approximate a full draw. Of course, there are more precise ways of doing this. This is just a quick approximation for the purposes of this webinar. Putting in 50 for these 2, both the upper and lower trays, you will see my degrees of freedom is still 3. That's because I have not set them to a specification. By doing that, I will just click the radio button, and you'll see this number drop down to 1. Now I have just 1 more degree of freedom. Something to do with the reboiler. I could put in a random boil-up ratio, but if I'm designing this fresh, I really don't know what boil-up ratio would give me a result. I could put in a temperature. Again, I don't really know what temperature will give me the specification I want. I could put in a reboiler duty, but again, as I said, you don't really know these numbers. You only know the product specification. So why not just specify the product specification? In this case, I'm going to add, and the specification I want to target is a C1 to C2 ratio. And this ratio is called a component ratio. I'm going to give it a proper name, C1 over C2 liquid volume percent. Click OK. And it allows me to specify any ratio I want. In this case, it's my liquid product, my NGL that I'm looking at. So I go on to the stage, I click on reboiler, and I'm only interested in the liquid, so I'm going to pick that. My ratio is C1 over C2, which means my numerator will be C1, methane. My denominator will be C2, methane. I'm more interested in the liquid volume ratio, so a ratio of flows would be in order. So standard liquid volumetric flow, because a flow divided by flow gives me a ratio. In this case, I want to get rid of as much C1 as possible from my NGL, which means I'm going to put a small value, for example, 0.008. Okay, so 0.008. What this means is for every 1 meter cube of ethane that comes out my liquids, I'll have a very tiny amount, 0.008 meter cubes of methane. I'll set that as a specification. And now my degrees of freedom is now 0. This will allow me to run the flow sheet. And as you can see, it automatically back calculates the temperatures that go on in this section that I did not specify at all. And the whole column is solved. Okay, so what can we do with a solved model? Well, we can look at some very important values. One of them is recovery. If I go into the demethanizer, I can go under recoveries and I can see, okay, my NGL, propane plus recovery is looking very, very good, almost 100%. Ethane recovery, on the other hand, is only 78%. It's not 90 to 95% I talked about. Well, this is because you also have to know the balance between ethane recovery and ethane rejection. If we look at our sales gas at the moment, you'll notice the heating value is very close to the lower limit of the specification, 900 BTU per standard cubic feet. If I were to recover any more C2, this value will drop below my specification, which means I can no longer sell it. As a result, this particular model is optimized in such a way that I meet the minimum requirements of my compressed gas while extracting out as much of the valuable C2 plus as possible. Okay, I see a question over here about how do I select the feed tray. Well, you could just selecting the feed tray is as simple as just moving this up and down. So if I wanted to change the feed tray to tray 7, you can re-execute it to see what changes happens. You can move it back down, re-execute it to see what changes happen. And selecting the feed tray is more of an art. So as Omar has mentioned, you just play around with it until you see a value you like. Okay, let's move on to what do we do with this NGL. Let's double click on it and we can see the composition. There's a very tiny amount of methane, mostly ethane and everything else. Of course, all these have their individual uses. You don't want them all mixed together. You can't send propane into your ethylene plant, for example. So how do we do that? That brings us to our next section. A fractionation train. So unlike the demethanizer, we don't really have to use any crazy technologies to separate out propane and heavier. It's all a basic column with some trays, some overhead condenser, some reboiler at the bottom. Reason being is methane is very difficult to remove from ethane, whereas propane and etc. generally has more reasonable temperatures for us to work with. So we generally go from lightest to heaviest. Let's see. We start with a deethanizer. A lot of this will be information dumps. I'm just going to highlight certain values that are important. For example, the deethanizer, you will notice it uses a partial condenser at about 20 degrees Celsius, which means it's going to be quite cold. You may not be able to achieve this with a simple air cooler. On the other hand, if we were to look at the depropanizer, the partial condenser operates at about 40 degrees Celsius, which is a much better value for air-cooled condenser. And you will also notice that the products over here Their specifications generally just say you need a lot of whatever it is. So for example, C2, you need 95% plus C2, and your C3 product is 90% or more C3. Okay. Next, we have the debutanizer. It just removes butane from the top, and you will notice a trend with the condensers. It goes from 20 degrees to 40 to 70. Because it's longer and longer hydrocarbon chains we're getting rid of, it's hotter and hotter. And as a result, the pressures also drop more and more. So it goes from 20 to 13 to 5 bar gauge. Same thing with the product. The only unique one we have for the Pentane Plus product is a reed vapor pressure to ensure it's allowed to be trucked around. And finally, because isobutane and normal butane has very different purposes, we can't just mix them together. We generally have a C4 splitter at the end of the train. And this C4 splitter, in contrast to the trend before, will have a lot more trays, and it generally has a colder, it requires a lot more trays because your IC4 and NC4 have very close boiling points. Finally, the product specifications we have for this IC4 and NC4 generally just say you need to be more than 95% of what it is. Now let's show this off a bit more on ProMax. Okay, so the NGL fractionation train is shown here, exactly the same as before. I'm not going to go too much in detail in specifying everything else. I just want to show you some of the cool things you can do with ProMax columns, because specifying, you don't just have to specify the things you must, like reflux ratios. You can specify direct product compositions if you would like. So let's start with the deethanizer. If we look under specifications, we see, oh, there's 2 degrees of freedom over here. 2 degrees of freedom, where did they come from? 1 energy stream here and 1 energy stream here. That's 2 degrees of freedom. The more keen-eyed people might notice, hey, what about this energy stream going to the pump? Well, that's already specified, because if you double click into the pump, you will see a pressure change as well as the efficiency has already been specified. So that takes away the degree of freedom introduced by this energy stream. So that's 2 degrees of freedom. I'm going to show you how to specify a condenser temperature. For example, if you have an actual plant that you're trying to fit, you will normally have a temperature meter at your condenser. And you want to build a model of that plant, you need it to match. You could go try your luck with different reflux ratios until you get the exact temperature. Or what is even easier is to just directly specify the temperature. So you can do that by using our phase property specifier. I'm going to give it a discrete name. I'm just going to say condenser temperature. Click OK. It brings up this page. Now, the stage I want to look at is condenser. It doesn't matter what vapor or liquid, I just want to see its temperature. So I press T, and that's temperature. As you can see from this extremely long list, you can specify almost anything that is a number in ProMax with this phase property. But of course, I'm only interested in temperature. In this case, I want to operate this condenser at 18 degrees Celsius. I'll make that a specification. And the last degree of freedom I'm going to use it on is a very similar one we have shown before, this C2 to C3 ratio. In the one before, we had a C1 to C2 ratio. All this is the next step down, C2 to C3. I'm going to select this as a specification and run it. You'll quickly see it converges. And of course, with these specifications, to make sure you get it right, always double check your answers. So for example, I specified my condenser temperature to be 18 degrees Celsius. So if I double click here, you see, yep, exactly to 18 degrees Celsius. Means I did it all right. Next, with the depropanizer, we have the same setup. One energy stream here, one energy stream here. That means 2 degrees of freedom. Double click, go into specifications. Sure enough, you will see 2 degrees of freedom over here. Now, what if I want to specify a recovery, for example? What a recovery means is how much of that feed goes to a certain location I want. Because this is a depropanizer, I want a certain amount of my propane to go on top, a certain amount of my butane to go below. In this case, I'm just going to add a component recovery instead. So component recovery. I'm going to say bottoms IC4 recovery, because IC4 is the lightest of the C4 plus. I click OK. It tells me, okay, where do you want this? I want this at the bottoms, as said here. And I'm looking at iButane. The recovery I'm looking at is about 95.1%, just randomly. I'm going to make that a specification. In contrast, I want most of my propane off the top. So in this case, I have already preset a 99.9% efficiency of propane to the distillate. I'll set that as a specification, and now I'm at 0. I can execute, and the column turns green. Once again, I want to make sure I have all these specifications set correctly. So let me go to the process data, look under recoveries, and sure enough, I specified 99.9% going with the propane, that's here, and 95.1% going with the butane, that's here. And as expected, by specifying the lightest one, anything heavier will have basically 100% recovery. So let's look at the next part with total condensers. So the total condenser in this case has one extra thing. So we have the same pump setup, which I've already mentioned is already pre-specified. So we have 1 degree of freedom, 2 degrees of freedom, but we actually have 1 more degree of freedom, which exists in this reflux split. The reason why this exists in the reflux split is because you can see here it's blank. I didn't tell it how much goes to the reflux and how much goes to the butane splitter. Okay. So in that case, how can I put that in? If I double click onto this column, you will notice under specifications, I only have 2 degrees of freedom. What happened to the last one? Well, let's just fill in these two first. I want a certain recovery, overhead C4 recovery of 99%, and bottoms IC5 recovery of 99%. Exactly the same thing as I did before. Okay. Now it's 0 degrees of freedom. I should expect to be able to execute this. I click on execute, nothing happens. I'll notice everything is still red here. That's because I've not put in a split over here. The reason why, one of the unique things ProMax columns can do is you can grab something that is outside of a column and still put it back in. So in this case, I know that this condenser temperature is about 71 degrees Celsius. And by using this option right here, subcooled temperature, which tells it that it's subcooled instead of saturated, I can take that degree of freedom and put it into the column. So I'm going to make this the specification. You'll notice by changing this degree of freedom remains 0. But over here, you'll notice suddenly all this is brown. And brown means you can execute. And by doing this, ProMax will automatically calculate what split you should expect here. So in this case, 77% goes back into the reflux, whereas about 23% goes into the C4 splitter. Once again, I want to double check that my specifications were correct. So my recovery should be 99.9 and 99. Sure enough, if I go to recoveries, 99.9 of everything below and 99% of iButane above it. The reason why 99.9 is special is because these two are supposed to be averaged out. Okay. Now, the last thing that you might want to specify in a column is purity. Sometimes you may not care how much of something goes up and how much of something goes down. You just need 99% purity of this product. In this case, what do? Well, this column has the same layout as the one before it. In this case, I'm going to add a component composition because that's what purity is. It's just a composition. Okay. So I'm going to say NC4 purity. NC4 is, of course, the bottom product. So the stream I'm going to use is the bottoms. Uses the molar flow. And the property I'm interested in is N-butane. It's the molar fraction that I'm interested in because that is the purity. And the purity I'm looking for is 95%. I'm going to make that a specification. And you can see I've already done something similar for the IC4, which is the distillate instead of the bottoms. And it uses the mole fraction, I-butane. I'm going to change this into a specification. And similarly, I'm going to set the condenser temperature so that I can pull in this reflux split and execute the column. And everything is green. So once again, after you convert your column, always double check your specifications are set up correctly. If I double click into my IC4 product under composition, you will see I have exactly 95% I-butane at the top and exactly 95% N-butane at the bottom. This will allow us to specify basically anything you want, really. If you are ever unsure of some specification you want to do in a column, once again, I want to reiterate that our service is free. Our service is really good. So if you ever had anything you wanted to specify, there's normally some way we can help you do it. And let me go back to my slides and round off with a quick summary. Today, I've talked about sales gas specifications and what kind of goals we're trying to hit, as well as how we can hit them using JT and expander thermodynamics, how they work. I've went through the different technologies that we use. For example, we use the JT rig just to control the dew point. We use a refrigeration to improve C3 recovery. We use a stabilizer to remove C1 from the liquid. And we use the turbo expander to remove C2 from the vapor. And of course, at the end, we also talked about how to separate out the valuable feedstocks to each one of them. So we don't want the C2 to the C3 and everything else combined together. So this concludes my hydrocarbon recovery and fractionation webinar. These slides will be sent out to everybody participating as well as everybody registered in a follow-up email. If you have any questions at all, please do not hesitate to email us after this webinar. But I'm also going to stay back for about half an hour. If you have any questions, I'm going to look back at some of the questions that you have been asking. And yeah, so if you have any questions, please feel free to ask them and I'll address them as much as I can. Okay, one person asked isenthalpic expansion in expander. So there are two types of expansion that goes on. Oops, let me get to the slide. You have isenthalpic, which is the JT valve over here. It goes vertically down. It's isenthalpic, which means constant enthalpy. And the second type is the isentropic one, which is constant entropy. The reason why they are different is because if we look onto ProMax, for example, and here, what's the difference you see between a JT valve and a turbine? Well, the energy stream coming out of it. Because a JT valve, you don't really get energy out anywhere else. Whereas with a turbine, you're able to extract work out of expanding the gas. And this work goes into recompressing the gas somewhere down the line. As a result, you will see a very different type of expansion and cooling. In this case, a JT valve is only able to hit a certain temperature, Whereas this one, you will notice when you're expanding with an expander, it drops its enthalpy from about negative 34.8 to negative 35.5. So the difference in enthalpy is because you're extracting work. Okay, I have some questions about the different layouts and stuff. So again, I'm going to send all these files out. But for example, if you look at the demethanizer, I've stated over here we have 18 to 26 trays at about 45 to 60% efficiency. And as for the different splitters, all of their trays and efficiencies are all listed down over here. So when we send these out as a PDF, this will be a very good reference for you to pick and model what you want. As for the diameter of such a process, if we look onto ProMax, and we look at the demethanizer, for example, we can actually specify, for example, we want 70% flooding on everything. We just do a very basic one. For example, oops. So as you can see here in the demethanizer, as expected, if I want about 70% flooding for the whole thing, my top fat part will be about 1.8 meters, and the bottom will be about 0.7 meters in this particular case. So the diameter is very, very, very specific to the flows you're looking at, as well as the composition, etc. And all of this you can calculate using ProMax. So in this case, the demethanizer has those values. Okay, I see a question about why do you specify C1 over C2 or C2 over C3? The reason why you want to specify those is it's a very easy way of specifying how much stuff you want at a certain location. So for example, C1 over C2 just says that I want very little C1 for every amount of C2 at the bottom. Generally speaking, these are also the specifications given by most companies. For example, over here, you can see the Y-grade liquid. The C1 over C2 must be less than 1.5 liquid volume percent. Generally speaking, these are the specifications they want to use. And yeah, we're just following the specifications that are given to us. Next thing. How to arrive at the split stream to reflux to C4 splitter. Okay. In this case, over here, I think I probably did not specify this, talk about this enough. So the reason why this is possible is due to our interesting quirk where this temperature over here that we specify is subcooled. What subcooled means is if the boiling point of this mixture is, for example, 75, I can be anything below 75. Why this is important? Well, if it is fixed as saturated, we no longer have control over what temperature we have here. Therefore, we cannot link the control of the temperature here to this. Because if it's forced to be saturated, we already know the pressure here. So we're not able to change the temperature at all because it has a certain composition. It will have a certain pressure and a certain temperature as a result. So this is one of the simulation tricks which allows us to extend control of what we specify here onto this. That's the one of the cute ways we can go about specifying. Let's see. How do you select the temperature for subcooling in a gas subcooled process? So in this process, generally speaking, you don't really specify the temperature as much as you just specify the pressure. So if I want to play around with the recoveries, what I can do is I can go to stages. I can change the pressure over here to play around with the recoveries. I can also play, most of the time, what you want to play around with is this split over here, as a different split will allow you different amounts, because if you put more liquid into here, your temperature will be slightly higher, but you will have more of it. And the temperature here as well. Over here, in this case, I'm selecting -85. And the reason why I select -85 is because of if you see here, the minimum effective approach temperature is 3 degrees Celsius. It's more obvious in the plot. You can see here, I can't really pick anything lower than -85, because if I did, what will happen is I'll have a temperature cross, or this approach will be too high. And if you're, too low. If your approach is too low, your heat exchange area will skyrocket, essentially. So you're often just limited with the temperatures. You just want it to be as cool as possible, essentially, without having a temperature cross. And part of that is also balancing the split, because if you have less flow here, the temperature will drop a lot more, whereas if you have more flow going to the subcool. And ProMax has a scenario tool, which we actually covered on Monday. My colleague Omar covered it on Monday, where we talked about how to use the scenario tool, which automates these kinds of case studies. So next, what is the turbine efficiency you have considered for this simulation? In this case, the turbine efficiency I have used is 82%. This value can range anywhere from 70% to 95%, I've seen. But if you did not know what your efficiency here is, you can always put in a performance curve. And then using the performance curve as well as your actual flow rates, we can tell you what your efficiency should be. So that's one way of doing it. But generally speaking, I just use a value from 80 to 90% if I'm just doing a quick model. So the 71.11 degrees Celsius is the temperature cooled that was solved through the block. Yes, that is correct. It was solved through the block. So I told it what temperature it will be, but it just brings it to that value. Well, close to it. How do you know your number of trays in a column is optimal? Well, this is a bit more of an art as well. What you can do here, for example, if you had this model and this is the model of your plant, you can grab all this, look at your specification, and then go into the column and just start removing trays. Because if you're able to hit your specification, you can always just like right click and delete a stage. And you just slowly remove trays until you no longer hit your specification. That's one way of doing it. And then obviously you also need some system robustness. So you don't want to work exactly at the limit. You want to work a bit for that, obviously, just in case of robustness. So what types of heat exchangers used over here? Generally, I've seen the more modern ones use compact heat exchangers. But admittedly, I've also seen shell and tube used over here, but the shell and tube heat exchangers are insanely massive because they can't get as close approach temperatures as, for example, a compact heat exchanger is. I've also seen, yes, with LNG plants, they use spiral wound ones as well. You can specify, you can rate most of these heat exchangers. For example, over here, you can see we do plate and frame, shell and tube, and compact. We can specify that. We can rate those kinds of heat exchangers for you. Tray efficiencies and number of trays, as I mentioned, is all listed in the document. You will receive this after the webinar has concluded. For example, this demethanizer is just right here, 18 to 26 trays, 45% to 60% efficiency. Obviously, these varies from plant to plant, and if you have a plant, we can fit them for you. Over here, the deethanizer, etc., you can see if the number of trays as well as the efficiency is all listed neatly in these boxes over here. We'll also be posting these into Ganang's LinkedIn. Right. Why are there multiple feeds in the DC1? Right. So the reason why you want multiple feeds is because they each serve a slightly different purpose. With the liquids, most of the liquids coming down here if we look at the composition, you will see the methane is 40%. Most of it is ethane and the rest. So you want to bring, you don't want to bring them at the top because it means they will wash everything along the way. But instead you want them nearer to the bottom. You have some stripping action with the side reboilers, so they can start the stripping action straight away. Whereas something, for example, going at the top is 92% methane. And this is the kind of thing you want doing as your quote unquote reflux going on with the demethanizer rather than having it all together. Additionally, if we were to put this, for example, further below, then more of your column will have to be very big, and that big head will be different. So in the case of the RSV, the reflux has to be liquid. So it will be similar to this, where instead of taking a subcool split from the LTS, you will take your compressed fuel gas and you will route it through here and completely condense it. It has to be basically almost all liquid. And you have some JT valve, and then you drop it down, because it's if you were to just put in vapor into the top tray, what will happen is all the vapor will just leave with the top, and you're not really having any vapor liquid interaction. You want liquid methane reflux action with your ethane, your vapor ethane, so that you can wash the vapor ethane back down. So if you were to not use the expander and you were just to use refrigeration, depends on whether or not you use a column. But generally speaking, the reason why you can't just use refrigeration is because you can't achieve these low temperatures. Like over here, we have negative 100 degrees Celsius. Propane refrigeration can get you down to negative 40 at the most. Even then, it's really pushing it. Negative 30 is negative 30 to negative 25 is generally what you're looking at. But yeah, you just purely refrigeration without an expander is not really that. It's not, you can't get cold enough. It will be impractical. You have to use something like ethane as your refrigerant, which is not ideal. It's very expensive. So in the actual design are splitters and mixers vessels. So these splitters will be like a Y splitter, and the main vessels that you have is the low temperature separator as a way of controlling level and stuff like that. You also have to know that there's actually a sump in the demethanizer too. So you have some like volume here and there. But no, the mixers, you might have a mixer Y, and or these two might just enter directly into the temperature separator. But you generally don't need a vessel to split. How to determine demethanizer pressure? That's a very good question. So one trick you can use in a simulation is if you are given a composition and you're given a pressure and you know it's saturated, you know its temperature, right? So for example, this overhead, you know the composition is going to be basically almost 100% methane. You can take that into account. You can add a bit of ethane, a bit of everything else. And that's your product, right? So you don't know what pressure you want, but you know what temperature you can cool it up to. So let me just draw a stream. I'm going to say my product, I know my product is going to be, for example, 97.5% methane, maybe 1.5% ethane, and 0.7%, 0.3%. Let's just say this is my product I'm targeting. This will give me the exact correct heating values and everything else, for example. Okay, so that's one specification. It doesn't matter what flow I have really, because I know I can cool the top up to maybe negative 100 degrees Celsius. That's the limit of my process. So under pressure, because I know what's coming out at the top will be a saturated vapor, which means it's 100% vapor. And there you go. You have your you have the pressure. Obviously, this pressure is not practical, so you will want to use a different temperature. Maybe if you use a negative 97. can start to see what pressures you can use. So that's one cheap trick of getting it. If you know what kind of composition you are looking for at the top and what kind of temperatures you can reach, you can see what kind of pressures you expect at the top. And once you expect whatever at the top, you can sort of get what you want coming down. You just generally need one temperature to select the pressure. So in this case, if we look at the stages, it's roughly 22 bar gauge. If I were to, for example, this composition, copy this. Oh, it has a bit of. Obviously, you wouldn't know most of these if you have a certain rough estimate of it. You can see at negative 97 degrees Celsius, which is roughly what I can cool it to, the pressure is roughly 22 bar gauge. So that also depends on what you know about your product. But if you do not know and you just want to try and error, you can always just follow this. So the pressure of the demethanizer is roughly 14 to 31 bar gauge at the top. Okay, someone asked, what kind of stuff do you specify in these kinds of exchangers? In this case, I just specified the temperature over here. You can also use solvers and calculators to find out what temperature will give you your required approach. You can do that as well. Most of the time, what we do is we pick a temperature, we put a solver in, and then we solve it to hit a minimum effective approach temperature of 3 degrees Celsius for compact heat exchangers. That's the one we generally use to be more realistic for design. If you have an actual plant that we are modeling, we would generally just put whatever temperature that stream is, because it doesn't, that's a much better fit. But if you're designing a new plant that doesn't exist, you'll want to solve for a low temperature approach. If you have any other questions, please do not hesitate to email us. We'll be sending, as I said, we'll be sending out the ProMax file as well as all the slides you see here, including this very important 2 pages with all the rule of thumb designs. And if you have any questions, please just email us. We'll be happy to help out modeling your unit if you have one of these units, or any units at all, really. So yeah, last question, does the LTS act like a vessel? Yes, it does have a demister and everything at the top. You can even rate it, size it using a ProMax. So for example, include the sizing and vertical 2-phase, and you can put in inputs to size it. And yeah, if you want your existing units modeled, please do let us know. We're here to help.